In section 3.1, there was that problem on mixture that I wanted to, I left off something. I want to make sure that we go back and fix it. This guy right here, when we were solving for A, the amount, I think, of salt that was in the solution, um, we said this implies that this is e to the t over 100 times A equal to all of that. And then right here, I left it off. I left off that e to the t times 100. It should have been here. So put it here, e to the t all over 100. And then from there, I'm going to divide it through, looking at this equation here. So if you will, I'm going to go ahead and just erase everything that I have under that and just fix it. So this becomes A of t is equal to the 100 times e to the t over 100 divided by e to the t over 100. So this is 1,000 plus c over e to the t over the 100. And then now we use the initial condition A of 0 equal to 0. So we have 0 is equal to 1,000 plus c all over e to the 0. So that implies that c is equal to negative 1,000. And the amount is 1,000 minus 1,000 over e to the t over that 100. So that's better. Okay. Thank you, Christian, for noting that at the end of class the last time. All right. Now the next problem deals with how Ohm's law was derived. I think that's a pretty good question in terms of where it comes from, and to be able to take a problem, examine the problem, apply what you know from the previous chapter to deduce that. Let's look. Is it not that one? It's this one. Number 29 in the in sections 3.1. There's one very similar in Weber sign as well. The model is given utilizing Chirkoff Second Law that simply says that the sum of the voltage drop across any circuit is supposed to be equal to the impressed voltage on each of the of those circuits on that board. So so the idea is that they're supposed to be getting the same amount of voltage. But what happens is sometimes the voltage drops depending on the direction or the orientation of that particular circuit, or sometimes the voltage may rise. And so in linear algebra, we looked at a system of equations in terms of solving for those currents on each particular, whether it's a resistor or some type of, well, we didn't use any diodes, but resistors and the so-called inductance. So here, this problem says you have a 30-volt electromotive force is applied to an LR series. Just a simple circuit that involves a resistance and inductance. Current in which the inductance is 0.1 Henry and the resistance is 50 ohms. Find the current. If the initial condition for the current is 0, at the initial time, and then determine the current as t goes to infinity. And that's basically what Ohm himself was dealing with. He was looking at the limit of that particular equation. You look at the limit, then the limit of that ultimum gives you Ohm's law. So we'll look at that. So here, this is the diagram, and so here we have 0.1 Henry, and then we have 50 ohms, and then the voltage there is 30. So this system can model the linear differential equation. Here, where L is the inductance, and R the resistance, and then E here we have 30 volts. So if we plug that information in based on what we're given from this particular problem, we have 0.1 times di over dt plus the resistance, which is 50 ohms there, times I is equal to the voltage, 30 volts. Now once you have that, then it's just a straightforward linear equation that we want to solve. So in solving the linear equation, you remember that this is the form is dy over, we used, it was dx, I believe, plus some p of x times y is equal to f of x. Do you remember that? Right. Okay. So if that be the case, then what that simply tells us is that you want to isolate that derivative. So here we want to divide through, well, this is just 1 over 10, so basically multiply through by 10. And so we have di over dt plus 500i is equal to 300. Well, it's already in that linear form, so we just now figure out the integrating factor. We said is mu is equal to e to the integral of this p of x, which is just 500, is in with respect to t, so dt, and we integrate that. That's just, this gives us e to the 500. So that becomes an integrating factor. So got to put everything in there. So this is e to the 500 t. Thank you. Thank you. Thank you. Yeah, that would really hurt after a while. Okay, 500t. This is di over dt plus 500 times e to the 500t times I is equal to 300 times e to the 500t. You know, the idea is that once you find the integrating factor, just multiply it to the entire equation. The left side becomes automatically the product of the derivative of the integrating factor and the dependent variable. So this is the derivative here with respect to t of the product of the integrating factor e to the 500t. The independent variable, the dependent variable, excuse me, is I. This is equal to this 300 times e to the 500t. Now integrate both sides, and when you do, the left side is just what's in the brackets there. So this is e to the 500t times I is equal to this 300 times the integral of 3 to the integral of e to the 500 t, dt. And you integrate this, this becomes 300 divided by 500 times e to the 500t. You have to use a u du there, let u equal to 500t, and du is that 500 du, so we get 1 over 500. So this is the 300 over 500 times e to the 500t, and then plus our constant. So we have e to the 500t times I is equal to 3 over 5 times e to the 500t plus c. Divide through by the e to the 500t. So we have I, or I of t, if you will, is equal to 3 over 5 plus c times e to the negative 500t. And I think it gave us the initial condition that I of 0 was equal to 0. So this here implies that 0 is equal to 3 over 5 plus c times e to the 0. When you solve for c, c comes out to be negative 3 over 5. And so the equation here for the current is I of t is equal to 3 over 5 minus 3 over 5 times e to the negative 500t. So then it says, what's the current as t goes to infinity? So as time increases, what can we say would be basically the boundary for the so-called current? Well, we just investigate the limit. So the limit as t goes to infinity of I of t is equal to the limit as t goes to infinity of 3 over 5 minus 3 over 5 times e to the negative 500t. Well, here as t gets large, this is 1 over e to the 500t. That goes to 0. So here, this part goes to 0, and so we have left the limit of a constant as a constant. Which is just 3 over 5. But if you notice, that we had the voltage was 30 volts and the resistance was 50 ohms, and this gives us, we know R times I is equal to E. That's Ohm's law. But isn't that what the limit is implying? Here, the limit gave us I is equal to 3 over 5. That is 5 times I was equal to 3. And isn't that what we have here. Yeah. So it's the limit. It's the limit of this this current that gives us Ohm's law. Now, the neat thing is that what Ohm's law is saying is that, you know, ultimately that's you know, what the circuit is trying to produce. So for typically any small amounts of time, you definitely want to use this formula here, right? That I of t is equal to 3 over 5 minus 3 over 5 times this e to the negative 500t. But ultimately, we do have that that the current is simply 3 over 5. Any questions? I think the next one was the question of a fallen body. This was number 36. I believe this one ties directly to the problem that I've given you. I want to work this problem and then try to give you maybe 10 minutes. I want to give you a problem that it follows this problem. So you get the idea from this number, and then the next problem you want to be able to see if you can solve it. And so what they do is they slightly change this problem a little bit. They change it a little bit, then they ask you a question. And they say, look, if we change this problem just a little bit, can you solve this problem with the same questions with parts A and B from number 36? So here, how high, they assume that there's no air resistance. The next problem that we'll give you, we will say that there is air resistance, and the air resistance is given by some type of proportion to the velocity. Basically, as the object goes up, its negative force of the velocity makes it slow down. So we'll look at that. But look at this one first. Suppose a small cannonball weighing 16 pounds is shot vertically upward, as shown here in the figure. And it's being shot from ground zero, so the initial height S sub 0 is going to be 0. Tells us that its initial velocity is 300 feet per second, so that's good to know. The answer to the question, how high does the cannonball go, depends on whether we take air resistance into account. Here, they ignore air resistance, and so our problem is, let's investigate this without considering air resistance, but in the real sense, there is air resistance. And so the next problem, we'll look at configuring air resistance into the problem, and then look at the difference of the answers. So here, suppose air resistance is ignored. If the positive direction is upward, then a model for the state of the cannonball is given by, here, the second derivative of the so-called distance. Here, the acceleration is equal to negative g. And back when we looked at in section 1.3, that was one of our models. And so obviously the velocity is the derivative, the change of the distance with respect to time. And so it says the last differential equation is the same as this, dv over dt. That's what we're going to use, is equal to negative g, where we take g to be 32 feet per second square. Find the velocity v of t of the cannonball at time t. We're going to find this formula for v of t, and then secondly, use the result from part A to determine the height s of t of the cannonball measured from ground level. Find the maximum height attained by the cannonball. So what we're going to do is use this, and we'll just use our calculus to solve. So here we have dv over dt is equal to negative 32 feet per second squared, but we'll just use that here for now. What I want to do is to find what they are asking me to find, and they're asking me to find the velocity v of t. So I'm going to separate the variables, multiply both sides by dt. So I get dv is equal to negative 32 dt, integrate. So I'm going to integrate dv, but that'll give me v, right? So the integral of dv is v. That's equal to negative 32 times the integral dt. Well, that gives me negative 32t plus here this constant, but this constant is with respect to the velocity, so this is v naught. So you remember back in calculus where you would just ignore that constant. Well, that constant is most important, right? Because they tell us here that the initial velocity was 300, right? So where do you take that into account? So here we have v is equal to negative 32t plus 300. And I guess we can write that as v of t. But this is for part A. So part B, it says use the result obtained in part A to determine the so-called height. How do we get the height equation from the velocity equation? Let's integrate, yes. If I take a position equation, that is distance, and if I take its derivative, doesn't that give me its velocity? If I take its derivative again, I get the acceleration. So here we were first given basically the acceleration. I took the integral of it because that's the antiderivative. Take the integral of the acceleration, I get the velocity. Take the integral of the velocity, I get the height or the position equation. Right? So here, s of t, what we're solving for, is equal to the integral of vt dt. That is, s of t is equal to, we had solved for part A, this velocity equation, so this is equal to the integral of negative 32t plus 300 dt. So s of t is equal to negative 16 t squared plus 300t plus here, this constant is the constant with respect to the so-called height, so this is going to be s naught. Well, it said that it shot the cannonball from ground zero, right? Didn't it say that? From ground level. So that means that the initial height is 0. So we have s of t is equal to negative 16 t squared plus 300t. Now the question is, here, find the equation for s of t. We got that. Now find the maximum height obtained by the cannonball. Right? Find the maximum height. Well, to find the maximum height, I need the time associated with the maximum height. Right? I need the time associated. Now, using calculus, how do we find the time? Well, I'm sorry, not using calculus, just using algebra, find the time, right? To find the height, we use calculus. How do we find time t? Well, one, how do you find the time t for the overall time, and then how do you find the time t for the maximum height? Now here they're only asking for the height, so how do you find the time associated with the height? Hmm? Okay, when velocity is 0. Well, you know, you notice that when the velocity is 0, you could be at the initial height, or you can be at the tip top. Then you can also be when that cannonball falls back down to the ground, right? That's already given, right? So no need to solve for that, right? So how do we get this? How do we get the time associated with the height? No, that makes sense. That does make sense. If you go back and look at the equation that we have, notice here that if you look at S of t, this is said to be the height equation, that if you set that equal to 0, it gives you a couple of things. It will give you the initial time, then it'll also give you the overall time that this particular cannonball traveled, right? But I want to get right down to what I want to get to. And what I want to get to is, give me the time. What's the time when I'm here? So how do I get that mathematically? And that can involve some calculus. When this cannonball goes up, comes down, but when it goes up to this top peak, right, it stops just a little bit, right? Then it dives back down. At that maximum, what is that called? I mean, yeah, we have that, yes. But what happens at that particular point? How do I get that point? Using calculus. I'm looking for this time when the height is at its maximum. How do we get it? Okay, let me ask you this, and then maybe if I ask you this, something should ring. What does the derivative mean when I set the derivative equal to 0? You have a tangent, right? You have a tangent, right? Good. So where is that in terms of this image here? When the derivative is set to equal to 0, that means that you said it's a tangent, but that tangent is also a what? What does that mean? Here, when the derivative is equal to 0, what type of line are we examining? Okay, straight, but it's horizontal, right? So do you understand that if I set the derivative equal to 0, the first derivative equal to 0, what you were doing back in calculus 1 was that you were saying that graph is going to top out. And where it tops out, that's where you're examining. You call it a critical point, right? That's what you called it. So if I set the derivative equal to 0, that means that the slope of the tangent is a horizontal line. That means that this ball is going up. It crests up right there. That's that tangent. That's what I'm looking at. That's the height. Then it goes back down. So if I set the derivative equal to 0, right, of this height equation, I can solve for t. So set s prime of t equal to 0 to solve for the time at the maximum height. But s prime of t is the same thing as which equation here? The velocity, right? The derivative of the position of that height equation, that's just v of t. So here, s prime of t, if you start there, doesn't matter, take the derivative, you still get negative 32t plus 300 equal to 0. When you solve for t is equal to 300 over 32. What does that give you? Here, 9.375 seconds. So the height the maximum height is s of 9.375 is equal to negative 16 times 9.375 to be squared plus 300 times 9.375. And so the height that you get there, you plug that into your calculator, and you should get it. $1,406.25 feet. Okay. Do you see how the understanding of the derivative set to equal to 0, how that plays a part in examining this object that goes up? Okay. Oh. S prime of t is equal to 0. We have a horizontal slope, right? The slope is equal to 0. That's what that means. So if I can find here that time, then I have the time that's associated with its maximum. And its maximum is a relative maximum that we examined back in Calculus 1. And so there at that maximum, here, I solved for t. I took that value for t, plugged that right back into the equation. I got the maximum height. Now, just just a note here. If you take S of t and set that equal to 0, you're going to solve for t, and that t that you're going to solve for is going to be that total time that this cannonball goes from this initial point here all the way back over here. Which, since this curve is symmetric, it's no more. The time is like 18, seconds. It's just 2 times 9.375. So what you could have done was basically at that end point not use the idea that the derivative set equal to 0 gives me my maximum. You could have just taken that position equation, set that equal to 0, solve for t, and that would have given you the time to be 18 point some seconds. Divide that by 2, and then plug that into your position equation, and that would have given you the so-called the maximum height. So either you could have used the algebra or the calculus to get the result. Either way would have been fine. Okay. Now, what if we change this problem just a little bit and look at what happens to the result? This is the next problem in the book. This was 36. So now the next problem, 37. Let's look at that. I want to see if I can maybe coach you through it, set it up, but then I want you to finish it. And I'll give you some time here in class to finish that, and then I'll come back and work one more problem, and we should be done for today. Let's see here. Put this problem in. So this is the problem that we just got through considering. So here, the next problem, it says repeat problem 36, but this time assume that air resistance is proportional to instantaneous velocity. It stands to reason that the maximum height obtained by the cannonball must be a little less than that in part B of problem 36. Show this by supposing that the constant of proportionality is K. They give that here to us, 0.0025. And so then it says slightly modify the DE in problem 35. Well, here we put number 35 there. And so what we're going to do is to try to repeat the same question that was asked in number 36. That is, 1, find the formula for the velocity, and then secondly, find the maximum height. Here, based on that air resistance is given to be directly proportional to instantaneous velocity. So understand here that I'm going to take this equation, that's what they're asking. I'm going to get dV over dt by itself. So just divide everything by m. So I have dV over dt is equal to g minus k over m times v. I'm going to plug in the values. K is given to be 0.0025. We have to solve for the mass, given that the weight, I think the weight was given to be 30, oh, not 32, but I think 16 pounds. Let's see. Yeah, suppose a small cannonball weighing 16 pounds. So we have that to work with. So dV over dt is equal to, here G is that negative 32 minus K, 0.0025. It's divided by M times V. Now the weight is 16 pounds. The weight is given by an equation as the mass times the acceleration due to gravity. So this implies that 16 is equal to the mass times 32. So the mass is going to be 1/2 of whatever the units that it's being used for. So here dV over dt is equal to negative 32 minus 0.0025 all over 1/2 times V. So you get dV over dt is equal to negative 32 minus 0.005 V. Okay. How do we solve this differential equation? That's what I would do. Set it up like a linear equation, right? Does that sound good with everybody? Was that an idea that you kind of saw when you saw that? Were you thinking linear? I hope so. And you weren't thinking that, you don't say anything because you're very smart. And so that's good too. And so I'm thinking linear. I'm thinking, something of this type, like dy over, we wrote dy over dx, but with real problems with respect to time, it's like dy with respect to dt, But I want to write it back in the form how it was given initially, dy over dx. Plus p of x times y is equal to f of x. So we want to write this problem in that form. So this is dy over dt plus 0.005 v is equal to negative 32. Right. We're solving this to solve for the velocity. Right? I want to get v of t by itself. Once I have v of t by itself, then I can take that equation and integrate that, and I can get s of t, that so-called the height equation. So here the integrating factor mu is equal to e to the integral of 0.005 dt. So this is 1 all over 0.005 times e to the, excuse me, I'm thinking about something else. E to the 0.005 t. How about that? We'll need the other part for the next part. So here, the integrating factor is this. So the left side is automatically the product of the derivative of the integrating factor times the dependent variable, which is v, is equal to negative 32 times the integrating factor. Integrate both sides, and when we do, we have left e to the 0.005 t times v is equal to negative 32 times the integral of e to the 0.005 t dt. Back before, I was doing this part and where I had the 1 over 0.00, and I was trying to go ahead and get the answer. But so this is e to the 0.005 t v is equal to negative 32. Here we integrate this, use the u du, so this becomes negative 32 over 0.005. Times e to the 0.005t plus some constant. The negative 32 divided by 0.005, what is that? 6,400, thank you. So this is e to the 0.005t, v is equal to negative 6,400 times e to the 0.005t plus c. Divide through by this e to the 0.005t to get v of t is equal to negative 6,400 plus c times e to the negative 0.005t. What is c? What is c? Because I can't get the height, s of t, until I know what c is, right? C is 6,400? Who told you that? Now, this problem is with respect to number 36, and I think in number 36, didn't it give you the initial velocity? So what's the initial velocity? $300, right? So here, what that means is that, because this problem is different in that it has air resistance. It has air resistance. So the way you configure these initial conditions is totally different than how it was before. Before, that air resistance was knocked off. And so here, v of 0 is 300. So it must be computed as such. So here I have 300 is equal to negative 64 plus c times e to the 0. So here I get c is 6,700. So v of t is equal to negative 6,400 plus 6,700 times e to the negative 0.005t. Now my question to you is solve for one, s of t, and then find the maximum height. The maximum height will be less than, I think in the initial problem we got 1,400 for the height when we solved for that previous problem. And so here the statement says that since there's air resistance, the height that you find here will be a little bit less than, oops. Well, I can't pull that up. I'm at the end of my rope. Okay. Let's see. Put it there. So Here's my question to you. Solve for S of t where S naught is equal to 0, at the ground level. And then when you find S of t, find the, it's not maximum. Find the time for the maximum height. And then find the height. I think with this information, with that velocity equation, that's the main thing that you need to proceed. Give you a few minutes with that. So you finished that problem. I think I gave you the note here that time is going to be 9.162 seconds. And that the height that you want to end up with is 1363.79 feet. Now the next problem came from section 2.4. I want to say section 2.4. It's a falling chain problem. You have the diagram here. You have a chain on a table. Some of the chain is hanging down, but then you have the rest of the chain that's tangled up there on the table, and that chain begins to drop, begins to pull. We want to investigate the velocity of this chain as it's falling. So here, a portion of a uniform chain of length 8 feet is loosely coiled around a peg at the edge of a high horizontal platform, and the remaining portion of the chain hangs at rest over the edge of the platform. You see the diagram there. Suppose the length of an overhanging chain is 3 feet, and that the chain weighs 2 pounds per feet, and that the positive direction is downward. Starting at t equal to 0 seconds, the weight of an overhanging portion causes the chain on the table to uncoil smoothly and to fall to the floor. If x of t denotes the length of the chain overhanging the table at time t positive, then the velocity is no more than simply the dx over dt, the derivative of the so-called position. And here it says when all resistance forces are ignored, it can be shown that a mathematical model relating v to x is given by this. Well, that's pretty good. They've done the hard work for us. They got a formula for us. But then it says rewrite this model in differential form. Proceed as in problems 31 and 36. Those were the problems where the differential equation, you want to see if it's exact, is not exact, but then you want to find that very funny looking integrating factor, and then you multiply the integrating factor to the equation, and then you solve for exactness. Find an explicit solution of v of x. Determine the velocity with which the chain leaves the platform, part B. I think the way that they want you to do it here takes a little longer. There's a quicker method, and let me set that up quickly. Just give me one minute to do that, and then I think after that you should be able to solve it. So we're given, let's look at that. This is x, v, and then dv over dx plus v squared is equal to 32x. Right? So what I'm going to do is to divide everything by that x and by that v, just to get the dv over dx by itself, and then to see if it resembles something that I can work. Does that look like anything? Yes, sir. It is Bernoulli. And so if I were you, I would solve it using Bernoulli. Let me just start it just here for a moment, and then I'll leave the rest to you. It's Bernoulli, so what I'm going to do is multiply everywhere v. So I have 32 over here by itself. So this is v dv over dx plus 1 over x times v squared is equal to 32. Let u equal this v squared. Because its derivative should pick up v dv dx. This implies that u prime is equal to 2v times dv over dx. So 1/2 u prime picks up the v prime. So I have 1/2 u prime plus 1 over x times u is equal to 32. Multiply everything by that 2. So I have u prime plus 2 over x times u is equal to 64. The integrating factor is e to the integral of 2 over x dx. That's just x squared. So the left side is the product of the derivative of the integrating factor and the dependent variable. That's equal to 64 times the integrating factor. Okay, that tells me it's time for me to stop. 64x to the third all over 3 plus some constant. You get u by itself, and then u was this v squared. You get v squared by itself, and then you get v by itself. And the only thing that you would need to be able to finish part A is initial conditions. Suppose that the length of the overhanging chain is 3 feet. So the initial condition is x of 0 is 3 feet. That's all you need to finish this problem, to get part A and part B, and my time is way past, and so I'm going to stop there. But those two problems you finish, and for this problem, I think since that was an even problem, let me give you the answer for that so you'll know what you're trying to get to. Now, that's an odd. It's odd. It's odd. So you can get the answer in the back of the book. Okay? Thank you. See Nazra if you have any questions.